Okay, so in this video, what I want to try and do is derive the Laplace operator for the hyperbolic trig functions, Shine and Cosh. So just to recap what those look like. So for Shine, we have f of t equals Shine, so that's just sine with an h, Shine at, is defined as half of e to the at minus e to the minus at. And f prime t, let's say, is going to be cosh. That's cos h at is just simply half e to the at plus e to the minus at. So if we plot that on MATLAB, we can see what that looks like. I'm just plotting the function here, the hyperbolic sine function, shine at, half e to the at minus e to the minus at. And the blue line here just represents the sine wave. Only the first positive quarter cycle and the first negative quarter cycle. So that's going to be pi on 2, and this is going to be negative pi on 2 over here. And the red line is just the hyperbolic function there, just plotted out there. And then similarly for cosh, we've got the cosine function, the first between the first quarter part of the cycle and the first negative quarter cycle, pi on 2 minus pi on 2, and we've got the shape of the hyperbolic cosh at function defined here as half e to the at plus e to the minus at. So that hopefully shows, just as a recap of what the Shine and Cosh functions actually look like. So now that we've plotted it on MATLAB, we know that Shine is just going to be, it's going to look something like that. And we know that Cosh is going to look something like that. And of course, the if we were to draw the sine function kind of going in, it would look like this, and then something like that. And then here, this is just the that would be the cosine function as such. So let's have a look and see if we can find what the Laplace transform of these functions are. Now, one property of Laplace is its linearity. So if we have, say we have two different functions, say f of t and g of t, and we want to know the Laplace transform of both those functions, it will simply be the Laplace transform of the first function plus the Laplace transform of the second function. So let's say we want to know what the Laplace transform of a f of t plus b g of t is. Well, we can say that that's just simply going to be the Laplace transform of a f of t plus the Laplace transform of b g of t. Now, a's and b's are just going to be the multipliers, so we can actually take that out, and we should be able to say that that's going to be equal to a of the Laplace transform of f of t plus b times the Laplace transform of g of t. And we're going to use this property here to derive what the Laplace transform of Shine and Cosh are, the hyperbolic trigonometric functions. And this is a very interesting property, a very useful property that we can use later on as well for any Laplace operator. This property of linearity. I forget whether this is called additive or commutative. Right, so we know from the work that we've done before that the Laplace operator of e to the at is simply going to be 1 over s minus a. That we know. If we find the Laplace operator of e to the minus at, then we should be able to use this property of linearity to derive what the Laplace operator of these hyperbolic functions are. So let's find out, let's try and derive what the Laplace operator is of e to the minus at. So that's going to be defined as a semi-infinite integral between positive infinity and 0 of the function, in this case e to the minus at, e to the minus st dt, okay, which equals semi-infinite integral of e to the minus at minus st dt. Okay, now let's take out the t. Let's come down over here. So now, between infinity and 0, we have e to the minus t, a plus s dt. And that it will evaluate to 1 over minus a minus s of e to the minus t a plus s, evaluated at the semi-infinite limits. So this will be 1 over minus a minus s. As t tends to infinity, e to the minus t a plus s will tend to 0, minus e to the minus 0 will be 1. Okay, so now we can come back down here, and that's going to be this thing times by minus 1. So this is going to end up as being 1 over a plus s. So we can say, therefore, that the Laplace operator of, the Laplace transform of e to the minus at is simply going to be 1 over s plus a. And the Laplace operator of e to the at will be 1 over s minus a. Now that we have this information, we should be able to use the property of linearity, which we've looked at over here, to find what the Laplace operator of Shine at is. So let's have a look at that there. So if we do the Laplace operator of Shine, sine h at, that should be half. I'm just looking at the definition of what Shine is. Half of the Laplace operator of e to the at minus the Laplace operator of e to the minus at. Okay, so we can say that's going to be half. Well, we know what the Laplace Laplace transform of e to the at is. 1 over s minus a, isn't it? 1 over s minus a from up here. Subtract the Laplace operator of e to the minus at, which is just going to be 1 over s plus a. And now, what we do is that we're just going to simplify this. So let's take another. We're just going to write that up again. So we're now saying that the Laplace transform of Shine at is going to be half of 1 over s minus a minus 1 over s plus a. Okay, so if we multiply the top and the bottom here by s plus a, we do the same over here but with s minus a. Sorry, this is a bit wonky. S minus a, and we'll stick s minus a on the top. Then we can say s plus a minus s minus a all over s minus a, s plus a. And then we can do half s minus s, so the s is going to cancel. A minus minus a is going to be 2a. All on s squared minus a squared. Okay, the halves are going to cancel with a 2, so we're left with a on s squared minus a squared. So now we've derived that the Laplace transform of the first hyperbolic trigonometric function, Shine at, will be a on s squared minus a squared. And a good way to remember that is if we remember what the Laplace transform of Sine at was. Laplace transform of Sine at was simply a on s squared plus a squared. So the only difference in going from the normal Laplace transform to the hyperbolic transform is on the denominator, instead of s squared plus a squared, it's now going to be s squared minus a squared. Oh, sorry, so you could see that got cut off there a little bit. Yeah, so that's a good way to remember it. Now, if we have a look at Cosh, let's see now. We know that Cosh at is defined as a half of e to the at plus e to the minus at. Yeah. So if we want to know the Laplace transform of Cosh at, it's simply going to be the Laplace transform of half e to the at plus e to the minus at. And now what we're going to do is use the property of linearity. And we can take the half out. That's going to be half of the Laplace transform of e to the at plus e to the minus at. And using the linearity property again, we can say this is going to be half of the Laplace transform of e to the at plus the Laplace transform of e to the minus at. So I'm just going to write that up again at the top. And then it's just a matter of simplifying. So the Laplace of e to the at plus the Laplace transform of e to the minus at is what we want. So this is going to be half of, well, we know the Laplace transform of e to the at is 1 over, what did we say it was? 1 over s minus a, wasn't it? 1 over s minus a. And the Laplace transform of e to the minus at is going to be 1 over s plus a. Same process again. So if we multiply this by s plus a and s plus a, and we do the same over here of s minus a and s minus a, we end up with half of s plus a plus s minus a on s squared minus a squared. The a's will cancel. So we're left with 2s on the top. That's going to cancel with a 2. So we're going to be left with s on s squared minus a squared equals the Laplace transform of the Cosh at hyperbolic function.